Welcome to Recording 1A in our series on solving systems of equations graphically for Unit 8, Chapter 8, Math 2200. Here we look at the number of possible solutions in a linear quadratic or quadratic-quadratic system. So in other words, if I have a quadratic function here and a quadratic function here, for example, how many possible solutions could I have? In this little screenshot, we can see that there are two. What about if it was a line and a quadratic? Think about that. Okay, I'll put you out of your misery. From Math 12.1. Remember, if it was two lines that were graphing, then we may have one point of intersection, just one. However, if the two lines are parallel, there's no way that they're ever going to cross over. So therefore, there would be no points of intersection. And if we had the same line twice, for example, if I was graphing y equals 2x plus 1 and 3y equals 6x plus 3, these initially look like they may be two different lines. However, if I take the second one and divide everything by 3, I wind up with the same line once again, y equals 2x plus 1. So in that case, I'd have one line overlapping the other, and they'd intersect everywhere. Infinitely many points, therefore infinitely many solutions. Now, what about if we had a linear quadratic? Well, if it's a line and a parabola, there may be no point of intersection. There may be exactly one point of intersection, so there would be one solution. Or there may be 2 points of intersection, therefore 2 solutions. Of course, remember, our parabola could open downwards as well, and our lines could be slanted negatively or horizontally, or perhaps even vertically. Now, quadratic-quadratic systems. I could have no point of intersection between two parabolas. I could have one point of intersection for the two parabolas, or I may have 2 points of intersection. But this does not describe all the possible ways that two parabolas could intersect. Let's see if we can think about other ways. Here's a little exercise. Sketch two parabolas which both open the same way but have no points of intersection. So I'll have, for the first one, my two graphs opening downward. I will sketch one graph, something like that, and another graph with its vertex below the vertex of the first one, but I'll also make it narrower, so there's no way it can ever catch up with the other graph and intersect it. So that's one possibility there. What about exactly one point of intersection, both opening the same way? So I'll start with the exact same two graphs that I have up here. Now, to have exactly one point of intersection, all I need to do is shift one of them. For example, I'll shift this one. And they share exactly the same vertex. So they have exactly one point of intersection. I could also have a situation where I have two parabolas just shifted so that they only intersect once, like that. Now, for exactly 2 points of intersection but opening the same way, I could start with those same two parabolas again that I had in part A and simply shift, say, the smaller one up above the, or I should say the narrower one, up above the wider one. And finally, for my infinitely many points of intersection, I simply have one parabola that is congruent to the other, and they lay on top of each other, like so. And there we have it, all the possible numbers of points of intersection between two parabolas. So there we have it. The possible numbers of solutions for a system of linear quadratic equations are no solution, one solution, or two solutions. For a quadratic-quadratic system, it's no solution, one solution, two solutions, or infinitely many solutions.